Welcome to my talk on Grokking Coroutines. I am Dan Liu. I've been working on Android for almost exactly 10 years. I believe it was like October 9th, 2009 when I got started. And I've been working with Kotlin for about 3 years. And this is a talk about coroutines, which starts with a picture of, that's some roasted delicata squash. And you're probably wondering why I have a picture of that up. It's not because it makes a nice C. It's because I cooked that. I cooked that about a week ago. So I wanted to start off talking about my cooking ability. I'm not going to be bragging here. I have a rather modest cooking ability. As you might expect from a programmer, I'm fairly good at following directions. So if you give me a recipe, I can, generally speaking, take it from start to finish and have something edible at the end. This is what I like to call a danwich. I make this about 3 to 4 times a week. It's like my go-to standard lunch. That's why it gets its own special name. It's not that special, but when you make a recipe about like 500 times, you become somewhat of an expert in like the stupid minutia of things, like how to perfectly arrange the avocado and whatnot. This is the back. The thing in the back is something my wife made. The thing in the front is an apple pie that I made. That's probably the hardest recipe I know how to make, just because pie crust is really difficult to work with, at least for me. So I have like a cookbook of maybe like 3 dozen recipes. I can make them all pretty well, but I don't really understand how any of them work. So for example, here's a vegetarian chili that I made on a pretty regular basis. It starts out with, you cut up a bunch of onions, you kind of soften those onions, you put in some spices, then you put in stock and tomatoes and beans and let it boil for about 20 minutes. And then it's at the 20-minute mark, you put in a couple teaspoons of sugar and a couple teaspoons of tomato paste. And then you let it simmer a bit longer. I have absolutely no idea why. Why does the tomato paste and sugar not go in at the start? Why does it take this time to wait? I don't know. But I'm not going to question it because I am not a chef. I have no idea why you would want to wait on this. I can just follow recipes. I can keep myself alive. That's about it. So this is my level of cooking. I love this shirt. I don't know if you can see it on this picture, but it says it's the Dan Liu Exchange. One of my coworkers lives in Ohio, and he actually lives close to the Dan Liu Exchange, and apparently his family friends with the person who owns it. It's like a catering company. So that's me being a faux worker at the Dan Liu Exchange. But you compare me to Gordon Ramsay, the stand-in for actually good chef, and there's quite a bit of difference between me and him. For one thing, I don't swear quite as often. Maybe that'll change in this talk, I don't know. But for another thing, it's not that he knows a few more recipes than I know. I know 3 dozen recipes. It's not that he knows 1,000 recipes. It's that he has a much deeper understanding of how cooking itself works. He's not working by rote. He can actually create recipes on his own. He can come up with things. He can improvise as necessary. And I don't need that level of understanding. I just need a level of understanding that keeps me alive through food. But that's his profession, is being a chef. So he has to have that level of understanding. So that brings us to what I should have a deep level of understanding about, which is actually programming, to bring this back to the world of code. Let's talk about Kotlin, in particular coroutines, because that's what this talk is about. And unfortunately, the reason I'm bringing up all this recipe stuff is because really for the first maybe year of working with coroutines, my level of understanding was that of recipes. I did not really understand what was going on beneath the surface with coroutines. So for example, who here knows absolutely nothing about coroutines? Raise your hands. Great, this talk will be great for you all. Who here could probably explain to someone what coroutines are? Now, keep your hands up if you could do that without using anything from Kotlin. Cool. Can you explain coroutines without Kotlin? Woo! One person. So that's where it bothers me, where it's I'm just trying to use this thing, but I can't explain it, and that really bothered me. So what does Kotlin say that coroutines are? They say essentially coroutines are lightweight threads. They've said this over and over again, which is great. That's what I want. I want an easier way to deal with threads. And here's like a kind of standard code example you might see. I've got a suspending function that requests some random URL. I don't know, it gets it from some like database on the disk. I have a suspending function that downloads an image, and a third function that displays that image. And then I can use this launch thing, and it looks like nice imperative code where I'm just like grabbing a URL and going and downloading it and displaying it. And normally this would be some sort of like mush of callbacks or streams or futures and promises, and it's kind of nice with this. This is sort of what Coroutines gets you, is this nice simplified code. But there's all these questions I would have around this that just like kind of bore into my skull, but I ignored for a while. Like, why do I need this scope thing? What is launch doing that's special? Why do these functions need the suspend keyword on it? Like, why does that make it a coroutine and not a coroutine? But whatever, this code is running on other threads, it's fine. But then, like, I saw this, another part of Kotlin coroutines is sequence builders. So this code here creates a sequence that can generate Fibonacci numbers. And all of the stuff inside the sequence curly brackets is a suspending function. And it has a special yield keyword which allows you to like yield up values to whoever is requesting it. But the interesting thing about this code is that you can't change threads on it. I thought the whole point of Kotlin coroutines was like to change threads, like to do concurrent code with other threads. And this one's saying you can't use other threads. It just didn't add up to me. And what I was really lacking was a good model of how this is working. What I was really working from was recipes that people had shown me for how coroutines works. But they hadn't ever actually explained to me like what the fundamentals of it are. I have a toddler. Here's him running around at the Minnesota State Fair. He is a good lesson in mental models because like he's just constantly trying to figure out how the hell the world works. Gravity is like the quintessential example of a mental model that babies form because like they take something and drop it, and they take another thing and they drop it, and they take a third thing and they drop it, and they're figuring out that like, hey, when you drop things, they fall. And not everything falls at the same rate. If you drop a tissue, it falls slowly. If you drop a ball, it drops quickly. So they kind of naturally intuit air resistance, and they know that pretty much everything, except for these weird balloons that somehow go upwards, obey gravity. So they're creating a conceptual model, and what I really want is a conceptual model for coroutines. There's this book called The Design of Everyday Things that it's really, really seminal work on how to do good basic interaction design, and it has this quote that I love. A good conceptual model allows us to predict the effects of our actions. Without a good model, we operate by rote blindly. We do operations as we were told to do them. We can't fully appreciate why, what effects to expect, or what to do if things go wrong. And that's essentially like the difference between recipes and understanding. When I cook, I don't have a mental model. I follow the directions. If something goes wrong, I have to order a delivery pizza that night. And that's fine for me as a cook. It doesn't sit well with me as a developer. I want to have that mental model for coroutines. So what I'm going to do in this talk is try to dissect the basics of coroutines, at least how they work in my head. And I hope that you get something out of that too. I hope this mental model helps you as well. So let's start with what are coroutines, which is like the point of this talk. It's probably good to start there. But I'm not talking about coroutines in the Kotlin sense. I'm talking about what are coroutines, period. Because coroutines are not something new. Kotlin didn't invent this. Neither did, there's this whole modern usage of coroutines. Those didn't even invent it. Coroutines was first coined as a term in, I believe, 1958 or so. So it's existed for a long time. Perhaps the easiest way to understand what coroutines are is to contrast them with subroutines, which is something that we use all the time and it comes extremely naturally to us. So for example, here I have this code where I can provide a list, it sums the squared values, so it adds all these up, but it does so by calling the square function. And whenever it gets to this line of code, it goes down, it calls to this function, the subroutine does its execution, it ends up going back to the same spot it came from. This is just very natural, intuitive to us now as code. We eat, sleep, and die through subroutines. Unless your app is just one huge main function, like heaven help you, you're using subroutines all the time. And it makes sense. It's very intuitive to have this routine call over. It starts at the top of the subroutine with some parameters. Then at the bottom of the subroutine, it returns some value back to where it came from. This is a very simple model. It turns out that this is a way for two functions to talk to each other, but this is not the only way that two functions can actually have to talk to each other. Like if you're thinking about it in terms of like assembly language, there's no where you're just jumping through lines of code. The fact that you have a subroutine is just by convention. You're just saying like, hey, when I jump to this line of code, I'm going to have these parameters loaded in these memory registers, which you will interpret as parameters. And then at some point, you will output in some other memory register and jump back to where you were invoked from. But there's a lot of other ways you could do this. So we could have instead coroutines. And the difference here is that coroutines, okay, maybe the one on the left is running and it starts executing the one on the right. Fine. One on the right executes a bit and returns back to the first coroutine. So far, so good. But actually now, what I can do is I can have the one on the left call back into the one on the right. And it resumes from where it last suspended. And we can just keep going back and forth here. Each one calling the one before it, just kind of zigzagging back and forth. You can create infinite loops like this. There's no reason that functions can't just like keep calling back into random points within each other. And that's essentially what a coroutine is. You just aren't limited by the specificity that a subroutine has. A subroutine, if you think about it, is just a very specialized version of a coroutine, where there's a particular in and a particular out. And a coroutine just allows you to jump back and forth. So a simple example of that is with like a consumer and producer model. We have these two coroutines side by side. The producer being the Fibonacci producer, and then the consumer being just something that prints those out. So if we walk through this, we go to the consumer gets to the has next, and it says, okay, what do you got for me? And it goes over to that, computes all this until it gets to yield. And then it says, okay, here's your first value. It passes that back to the iterator. It says, okay, great, I have a value now, I can operate again. It goes back around to where the iterator says, okay, now what do you got for me? Then it goes back to where the producer last was, right after that yield line. Starts executing again until it gets back to yielding. The yielding passes back to the iterator. And again, now the consumer is resuming from back where it last stopped as well. And now we have this infinite loop that's going to keep just going back and forth forever, producing Fibonacci numbers until we get some integer overflow issue going on that makes it not very valuable anymore. So there are two interesting things to note here. The first is that they're sort of mirror images of each other. Like neither one of them is really the parent or child of the other. Like with the subroutine, it was really obvious that like one of them was the parent calling the subroutine returned back to the parent. Here, neither of them is really dominating. Like the consumer, okay, it is printing out values and it is nothing without the producer though. The producer is producing values, but it just stops unless someone else is consuming. So they're kind of mirror images of each other. And the second interesting thing is that they both have this point where they stop executing and pass control to the other function. So in the case of the consumer, it's when it's asking if the iterator has more values. In the case of the producer, it's when it's yielding up that value, waiting for someone else to take that value. And at both of those points, there are these local variables that it will capture and figure out like, oh, this is what I'm storing here for when the next time that I resume, I'll still have these variables around. And so what these functions can be thought of is as suspending functions. They can suspend their execution, pass control off to the other function, and then when this function needs to be resumed, they know to resume back at that point where they last suspended with all of the local variables intact again. And in fact, if you go into the IDE and you look at the code for this, there's this cool little symbol here which I didn't know about for like a year that actually shows you where in this suspending function it will suspend. So like that point right there, that's where this function might suddenly stop operating while it yields up a value. And another thing to note about this is that this isn't like some weird crazy concept, the idea that you can suspend execution and like save state. Like you can get that really easily if you just like write a class. Like you can have a class that like, oh, look, it's got all my local variables. Excuse me. And every time I call next, it operates, and then essentially the class is then suspended again until it's next called again. But I would say that The function version of this is a little easier to understand, and also I don't need to keep track of like which variables I actually need to hold on to for the state. And on top of that, that was a simple version of the Fibonacci. This is like the version that usually is shown in Kotlin, like it's in the Kotlin examples repository. This version actually has multiple yield points. It has multiple suspension points. Whereas the other class would be kind of a pain in the butt to do multiple suspension points. So anyways, what is a coroutine? It's essentially functions that can suspend. Suspend and then pass execution back and forth to each other. Why would we want to use coroutines? Like, that's a neat trick. You can suspend a function in some weird way that's not normal. Well, really, it just becomes like another tool in your toolbox. That's like why we crawled out of the primordial ooze of assembly language in the first place, was to like write code in different ways. But like, what ways can you use this tool? Well, there's two ways that I think Kotlin really focuses on. And the first is generators. That's pretty much what all the examples I was giving up to this point. But the other is concurrency. Concurrency is the ability to like do more than one thing at a time, to be able to multitask. And typically, I think, especially as Java developers moving over to Kotlin, when we think of concurrency, we think of threading. We think of, oh, we want to be able to do multiple things at the same time. That's what threads are for. But why is it that we think of threads as being the solution to the concurrency problem? Well, it's because normally we have all these blocking functions that we're running. So if you've read Douglas Adams' like Meaning of Life, he has this computer that takes 7.5 million years to compute the meaning of life, which turns out to be the number 42. If this is a blocking function, I have to wait 7.5 million years for it to finish executing. That sucks, because I want to do other things with my computer in the meantime. If you have a thread, this is easy. You just fire off, calculate meaning of life on another thread, and then some scheduler is going to figure out, like, I don't need to give it all the CPU time. I can split that time between it and other things. But let's contrast that with a non-blocking function. So if you have a suspending function, that means that it can operate to a certain point and then stop executing and give control to someone else. So now it's no longer saying that, like, I'm going to monopolize the time given to me when I'm called. So what this results in is you don't actually need another thread in order to do more than one thing at a time. So if you look at it like a line, if you have a blocking function that's doing some I/O, let's say, it's running, and then when it gets to that red portion, it's like making a network call or something. And at that point, I'm just waiting for the server to respond. And if it's a blocking function, then I just have to like spin on a while loop waiting for the server to respond. I just have to wait. But if we have a suspending function, or a non-blocking function, it can operate. And then when I go out to the server, I can say, hey, I don't actually need to be running for a bit. Like, I want to run, 10 milliseconds from now to check to see if the server's responded. But you can go off and do something else for a bit. And in that time, you can actually go do other work. And now I have multiple streams of tasks going at the same time, essentially. Like, one of them is paused, sure, but like you're essentially concurrently doing two things at once. And that's really powerful. You can do some really cool things. This is like probably the most complicated slide in this entire talk. But basically, what this slide is doing is using Kotlin Coroutines to execute two functions at once, concurrently. And it's doing it all on the same thread. It's doing it all on the main thread. And when you actually run this code, if it was not able to interleave work, what you'd see is it print out the first start and end, and then the second start and end. But that's not actually what you see. When you run this, sure, the first starts first, and the second starts second. That's what we'd expect. But because the second had a shorter delay, only 5 milliseconds instead of 10 milliseconds, it ends first. And it's able to interleave this work. You can do this with like as many asyncs as you want. It's able to interleave this even on a single thread because it's able to pass control back and forth to each other. And this is essentially the difference between threads and coroutines, is that threads do something called preemptive multitasking, where it does not know what each thread is actually up to. Like, it doesn't know that this thread is waiting for I/O. It doesn't know that this thread is like showing the UI. It just has like some ideas of like, well, this UI thread's really important, so I'm going to schedule a lot more CPU cycles for it. This I/O thread's not very important, so I'm going to not schedule that many cycles for it. Whereas coroutines can achieve multitasking by cooperating with each other. It feels like, yeah, let's cooperate. Let's get through this political logjam. You will work for a bit, and then they will pass the baton to this other person, will pass the baton to this other person, and they can do a bunch of things concurrently without actually having to have any sort of preemptive multitasking going on. So coroutines are like lightweight threads. Like the metaphor makes sense now. You're doing multiple things at the same time, but you're not actually having to use threads. Why would you care about this? Well, if you went to the other talk at this hour, you'd be learning about Kotlin multi-platform. Kotlin's expanding to more and more platforms. Coroutines essentially were the way for Kotlin to say, like, how do we solve this concurrency problem when we're going to have concurrency on like a whole bunch of platforms? Some platforms of which might not have threads. Oh look, we have this other thing, cooperative multitasking, that can also work. And that's the model that they came upon. All right, so we've gone over what coroutines are. We've gone over why we were wanting to use them. Let's talk about Kotlin coroutines. Let's finally get around to like that topic a little bit. So I showed this slide at the beginning. This example is going to keep coming back to haunt us. The thing is that this is not really basic Kotlin coroutines. Most of the stuff here, besides the suspending keyword, is not built into Kotlin by default. Most of the stuff here is actually in a Kotlin library. Because the way that one of the design philosophies behind Kotlin is to try to make like the core library as minimal as possible and then build on top of it using libraries. Because libraries are so much more flexible than core APIs. Like in a way, Kotlin itself is a response to the fact that Java is loaded with like decades of baggage. And it's really cool that Christina gave a talk earlier about like all that baggage and whatnot, like why we'd want Kotlin, a new Kotlin. So the way the coroutines are set up in Kotlin is that there is a standard library and there's a Kotlin coroutines, which is built into Kotlin and in the standard library. And then there's a Kotlin X coroutines library that's built on top of that. But this graph doesn't really show the relative size. It's more like this. Like the stuff in the core is really tiny. And I'm going to go over basically all of it right now. Like that's how small it is. The first and most important thing is definitely the suspending keyword. The suspending keyword marks that a function can suspend. It can have this magical ability to stop its execution, pass off control to someone else. So that's the first thing the suspending keyword gives you, the ability to suspend. Second thing it gives you is the inability to call it from non-suspending functions. So if you try to call it from a non-suspending function, the compiler yells at you and gets mad. And this is possibly the biggest WTF moment for me with coroutines in general, which is like, how are you supposed to start a coroutine? All right, if suspending functions can only be called from other suspending functions, and I have a non-suspending function, how is that supposed to call a suspending function? Like, is this turtles all the way down? If I'm going to use coroutines, do I need to make every one of my functions suspending functions? So that like that suspending function can be called by this one, and then like my main, I don't even know what I'm going to do with main, but like does everything have to be suspending? No. There is a connection point between these two lands. There is like a wardrobe that you walk through and you go from the boring state house manor to Narnia. And that is this function called startCoroutine. And it's like, I wish someone had told me this existed, because I was like, how do you start a coroutine? It's just like, oh, there is a function called startCoroutine, the end. Great. It's got kind of a weird method signature. The method signature is designed for the library, essentially, but you execute it's an extension on a suspending lambda. It's a little weird. So if you have a suspending function, you can refer to that suspending function, call startCoroutine, and that coroutine starts. Great, that's it. That's the second thing that the coroutine library core, or not coroutine library, this is the second thing that core coroutines provides, is the ability to start coroutines. There is also a create coroutine function, which allows you to create the coroutine, but not actually start it just yet. It'll start at a later date, but fine. It's pretty much the same thing. That's it. That's how you start a coroutine. But there is this like parameter here this completion parameter called a continuation. So what's the deal with that? And why do we need it? Well, let's look at the interface. The interface has two things in it, essentially. It has a context, which I'll go over later, and it has this resume with function. Resume with some result. All right, what is result? Well, result just holds a value, any value. That's kind of boring. Really what it holds is like a value or an exception. It's just for optimization purposes, it just holds an any, but like it really holds one or the other. And in fact, there are these extension functions that kind of better illustrate what this whole thing is trying to get at. So if you could rewrite it like this. We have a continuation, and we have an extension function that says resume with a value or resume with a throwable. What does this look like to you? Having a resume with a value and a resume with an exception. Yeah, looks like a little bit like a callback. On success, on failure. Interesting. So if we start a coroutine with this, we're essentially providing a callback for how to return the results back. And it turns out that you might be like, okay, where is this callback going? Because when I write these suspending functions, there is no place for this callback. I don't call it callback. That's what you think. When this code compiles, it turns into this. It adds a parameter at the end, which is a continuation. Every one of your suspending functions ends up with this continuation parameter at the end. So I'm taking all of these callbacks so that everything can be calling back. All these suspending functions that you've been writing are actually just calling back to each other. And there's a great talk that goes into more depth about how the internal state machine works, but it's basically all callbacks. And if you try to if you actually try to include both those lines of code in the IDE will yell at you because it'll say that there's a JVM overlap. Like they have the same method signature. And you'll be like, what the hell? They certainly don't. And they're like, no, it really does. Because when you go decompile the bytecode, that's what you see. So anyways, what I'm saying is that coroutines are just callbacks, which you know and love. And this felt a bit of a betrayal when I first learned this, because I was thinking that like, coroutines. I am coroutines, the great and powerful threading machine. I will have concurrency. Do not look at the man behind the curtain. But why is this actually okay? Why is this okay? Because we get to avoid callback hell. If we had that same example before, we have to do this like the pyramid of doom as you get further and further indented and then further and further out. And this is just showing it if we don't have on failure. It gets a lot uglier then. It's showing it if we don't have loops or some crazy shit like that. Compare that to this. It's nice imperative code. It lets us, calling coroutines lets us write this weird concurrent callback code as if it was imperative and much more intuitive. That's really cool. And then the last thing I want to talk about from the standard library is context, which I mentioned. It's another thing that comes along with continuation, is this context object. What does it hold? Oh yeah, what is it? It's just a store of key value pairs, basically. And what's in it? In the core library, nothing. It's there because it's very useful. And again, like what Christina said, pragmatic. It is very pragmatic to have this coroutine context here. I'll explain why later. But what have we learned about the coroutine core library? We have the suspend keyword, we have continuations, we have coroutine contexts, and a couple of other minor things I'm going to just gloss over. But it's really not much more. It's like 2 or 3 more functions that I have not mentioned that aren't really that important for my purposes here. So it's a very, very tiny library, very, very tiny thing. Let's talk about the library now, that huge bulking thing. We want the library because the core implementation is ugly as sin. Like, this sucks. Who would want to work with this? This is a nightmare. What we really want is that code example at the beginning, because that was the cool code that everyone got to read through. So I'm going to try to break down this code and show you how we got here. So the first thing we want to talk about is how do we start a coroutine? Because again, startCoroutine is a nice explanation for how we get from non-suspending to suspending functions, but it's not very practical. Well, it turns out that Kotlin provides this launch function. And that's it. Call launch and there's a lambda. Now you're in the suspending keyword world. Great. It's so simple. I love it. You call launch, you do something, the end. The one point of confusion for me for a long time, though, was like, how do I actually get a result from this? Because launch doesn't return a value. It returns this thing called a job, which lets you cancel, but it doesn't return like your T. It doesn't return your generic value. So it's like I want to calculate the median of life and I want to display it. How the hell do I display it when launch doesn't actually give me the value back? Well, it's really simple. You just call a callback yourself. You can just call your own functions in here. That's it. And the cool thing is that like you can call it multiple times. Like if you have some show progress, like if you're downloading something, you can call show progress multiple times inside it. It's all very intuitive. Anyways, that's launch. That's pretty much the way you start coroutines. Second thing you might have noticed me putting over and over again is that launch doesn't exist in a vacuum. It keeps being called on this variable that I created called myScope. What the heck is this myScope thing? Why is there this coroutine? It's known as a Coroutine Scope. Why the hell does this exist? Well, there's a really good reason for that. Let's imagine a world where we didn't need it. And this is actually the world of coroutines as they originally existed. And I can just launch a bunch of things. So I can, somewhere in my code base, I can launch task 1, task 2, and task 3, and they're taking their grand old time somewhere doing something. The problem is, what if I want to like cancel them? What if I want to stop them from working? Well, like I mentioned a bit ago, they return these jobs. So I can take job 1, 2, and 3. I store them somewhere in my class. And, a bunch of stuff happens. And at some point later in the life cycle, I decide, oh, we're done. We're not displaying that screen on Android anymore. We got to cancel all of them. This is a huge pain in the butt. I don't know how many people here have worked with like RxJava or any other sort of stream-based thing, but there's like so much bookkeeping to be done with getting rid of your subscriptions. It absolutely sucks. And it's so incredibly error-prone. What we kept running into, I even wrote a library to try to solve this, and so I'm like a little embarrassed that like they came up with like a 100-time better solution here. But like you want some way to force people to do the right thing and for everything to cancel when you want them to cancel. And so that's essentially what coroutine scopes are for. It's just ways to like group coroutines together so that they can operate as a unit. And so, okay, I create a job, I create a coroutine scope that uses that job. Then, whenever I launch my tasks, I don't need to keep track of their jobs anymore. They just get naturally added to the scope. And at the very end, I can cancel that job. And everything inside that scope gets canceled as well. And this is kind of a simplistic example of how scopes work. The real power of them comes from when you're dealing with like nested coroutines, but I don't really have time to go into that. But like it's very common nowadays, like for example, Android to have like, okay, I've got a job and scope, and then like when the activity goes away, I destroy everything, and then it nicely cleans up everything in a very nice manner. And what it's called is structured concurrency. It's kind of like a new up-and-coming technical term that I feel like we're probably going to hear about more and more. It's basically concurrency with boundaries. But the real problem here is that at any time, I can call launch, and I can create this other thread that's going to go do something, and I have no idea like what's happened. It's like I've taken my kid, and I've kicked him out the door and be like, go, see you later, bye. With structured concurrency, I get to say like, be back by dinner, all right? It's really, really powerful. And because we require a scope in order to launch a coroutine, it forces you to do the right thing. It doesn't let you shoot yourself in the foot, which is really nice. There's this amazing article, which I'm going to link twice in this talk. This is written from someone who writes a Python library that also uses structured concurrency. This article like blew my mind. It's so brilliant. And I encourage like everyone to read it because it essentially compares unstructured concurrency to go-to statements in a way that I feel like is very compelling. And it's basically like when we got rid of go-to statements, our lives coding got a lot easier and we could do a lot more things. In the same way, if we can get rid of unstructured concurrency, our lives are going to be so much simpler with structured concurrency. So I love that. I'll put that link up again later. So what about threads? I've been talking about coroutines, cooperative multitasking. I don't need more than one thread. Yeah, unfortunately, you kind of do. Like, for one thing, it's really exhausting to write everything cooperatively. Like, sure, you can have every function be able to like pause themselves and go call some other task when the other task needs it, but like actually coordinating that is a huge pain in the butt. It's nice to write like these 10 functions in a row are just going to execute and not pause during them. You can't take advantage of multiple cores. Like we can't make computers any faster now. We can't make cores any faster now, so like we just put more and more of them. So you want to be able to take advantage of that. And sometimes it's illegal. Sometimes it's against the law. Certain code requires you to execute on certain threads. In particular, like when you are writing a UI-based application, almost every UI framework operates in such a way that everything that has to do with the UI operates on some UI thread. So this has this nice effect of like avoiding shared mutable state between threads, which ends up being like a massive headache. So we want to execute on things on other threads. Do you remember that coroutine context thing that I mentioned that like will actually matter later? Well, like we can store whatever we want. And in fact, that's how Coroutine Scope works. It's storing like the job that can cancel later. Another thing we can do is we can store which thread that we want the coroutine to execute on. So in this example here, I'm calling this with context method and providing it a dispatcher, an IO dispatcher. And the dispatcher is essentially a way of saying like, I want to dispatch this on this particular thread. And bam, that's it. Now we have code, suspending functions that can execute on another thread, which is great. That's all we wanted in the first place. Why was I talking for like 40 minutes before this? I want to clarify something that confused me a lot, which is that there is this metaphor that was talked about at the beginning that coroutines are like lightweight threads. That's a metaphor. Coroutines are not lightweight threads. They're like lightweight threads. There is a feature in the Kotlin library which lets you execute coroutines on whatever thread you want. So that was like a large point of confusion for me when I first started working with coroutines too. It's like, are coroutines threads? No, but they do let you do a lot of stuff with threading if you want to as a feature. All right, so let's review. What have I gone over here? Coroutines are suspending functions, essentially. Suspending functions happen to be useful for concurrency, for doing concurrent work. The Kotlin core provides the ability to do coroutines, just the bare minimum to be able to get coroutines off the ground. And then there's a Kotlin coroutine library that adds a bunch of practical functions for coroutines, of which I went over a small smidgen of them. So what now? Because I'm getting to the end of my slides here. There's like so much more we could talk about. There's like compatibility. How do you work? Once you start using coroutines, it's not like you're going to convert your whole code base to them immediately. There's a lot of asynchronous code I'm sure that you have right now. How is it supposed to operate? How are we supposed to interop between coroutines and old async code? Composition. How do you concurrently execute multiple suspending functions? Like how do you go from concurrency to parallelism where you actually have two things operating at the same time? Cancellation. How do coroutines actually stop? Exception handling. What happens if something goes wrong? You need to handle that. Then you have flow channels and actors. The joke being here, I don't understand what actors do still. I think I'll have time for questions. Don't ask me about actors, please. So really what I've done in this talk is I barely scratched the surface of like what coroutines can do. My hope is that you understand coroutines at a more fundamental level that you can then build on. To be able to look at these topics and be like, oh, I understand why they set up cancellation the way they did. Like I understand why it's like cooperative cancellation in coroutines because this is actually how it's working under the hood. It's actually using these callbacks and stuff. It's actually suspending these functions. But where do you go for more information? I think one of the best places to get just a pile of links to look at, the Kotlin X Coroutines library has a documentation section, and that documentation section links to a whole bunch of talks and articles, and that's just like a treasure trove of information. That's like a good place to start and then fan out for what you want to know about. Roman Elizarov, we hope I'm pronouncing his name correctly. He's one of the team leads at JetBrains. He is also like one of the main spokespeople. He's worked, as far as I know, on all of Coroutines. He's the main spokesperson for it as well, and he's given, like every one of his articles and every one of his talks are worth watching and reading. Like, it's all fantastic. I highly recommend it. If you work specifically on Android, because I'm an Android developer, Sean McQuillan put out a 3-part series of articles recently on how you specifically use coroutines in an Android context, which I think is really good and really worth reading through. And again, I'm going to link to the structured concurrency blog because I just think it's brilliant. I love it. I can't push this article enough. Anyways, so that's pretty much all I had. We have like a couple more minutes. Does anyone have any questions?
What's the difference between asynchronous code and then coroutines? Is it basically the same?
What's the difference between asynchronous code and coroutines? That's a deeply philosophical question I'm not sure I'm ready to answer. I feel like it's maybe just one of terminology. I think you could say they're essentially the same, because you could say like, oh, coroutines lets you run things concurrently, and asynchronous code is all about like running things concurrently. I'm not really, I don't know that I'm like confident enough. That's the sort of thing where I'd sit down and like read 10 Stack Overflow posts about people arguing over what the exact term asynchronous means versus the exact term concurrency. So I'm not, sorry, I can't give a really solid answer there.
Have you started using coroutines in your production code yet? And if so, where did you start?
Have we started using coroutines in production code and where did I start? Yes, most certainly. The place we started was with metrics, actually. It was really handy because with metrics, we often want to like, all right, you clicked a button, great. We want to gather data about like, which button did you click? And some of that requires database accesses. And like, we don't want to slow down what you're actually doing to do all this metrics crap. We want to do this somewhere in the background. So it's really handy to just be like, hey, coroutine, go and do this. Launch is perfect for that. When you call launch and it's like, go do the suspending function, I never want to see you again. It's perfect for code like that and a great way to really dip your toes in. And now we're using it more and more. Like we actually just switched to using Work Manager. Well, not entirely. I don't know, sign up for the beta, you'll get the new Work Manager soon. Work Manager version of Trello Android. But like, Work Manager has a version of it that works with coroutines, so we're doing that. Yeah, we're using it in more and more places. I think I saw another hand.
How does this compare to the reactive libraries? Can we start moving away from some of the reactive libraries toward coroutines, or is there some other thing we're missing?
Yeah, so how does it compare to reactive libraries? That's a very good question. So at first I was like, they're completely different things. And I think the reactive libraries were very misunderstood at first, because I think a lot of people, and I'm very guilty for having propagated this idea myself, thought of the reactive libraries as like, ooh, a way to do easy threading on Android. It's really not. Like the fact that it can do threading stuff is like a side effect. And in the same way that like the fact that Kotlin Coroutines does threading is like just a library implementation feature. It's really all, like really reactive streams is all about streams of data and how you handle them. And coroutines at their basest is about concurrency. And concurrency doesn't really have anything to do with streams of data. However, they have added these things like flow and channels. Flow and channels get much closer to what reactive streams are doing. I have not studied them enough to really confidently say, but my suspicion is that flow basically replaces reactive streams. That's kind of the rumblings that I hear. And in fact, it's pretty easy. There are interop libraries which allow you to take like Rx streams and turn them into flows that you can then use. So I think, yes, the base coroutines doesn't really have anything to do with reactive streams, but these things that we're adding on top of it do. And that would be what I'd check out.
Thanks.
There's another question somewhere?
Yeah, just to expand on that. So off the top of your head, can you think of an Android example where maybe we we're pulling in all of RxJava just to do some simple asynchronous thing where coroutines blend itself nicely to.
Oh, I have a million examples of that in my own code base. I mean, the quintessential example being like, you click a button and you go make a network request. Like you click a button and then like you go for search results or something like that. And then those search results populate in some recycler view on the screen. Like before you'd be like, okay, I'm gonna have a button stream, and that stream of clicks is going to flat map into some retrofit call, and that retrofit call then is subscribed into displaying on the recycler view. And like, that's fine, but it's not, like the clicks is not really a stream that I care about. I care about this event that like, I wanted to just look for things. And for me, like coroutines makes a lot more sense there. It's not a stream of data I care about as much as I want to like, just do something once. So. Go ahead.
I was just going to say, sorry, just to follow up on that, like if we were diving into our own Rx code base, do you think like maybe something that's just asynchronously returning a single is probably a good candidate to go look to see if we can replace with coroutines?
Yeah, so it's something like is replacing asynchronous singles a good place to start with coroutines? Sure. I think so, although it depends a little bit because like, again, remember I mentioned that the launch doesn't actually return a value? Like you have to have some replacement for like, where am I gonna spit this value out at the end? And that's one thing that's, that Flow gets at that base coroutines doesn't. One cool thing with reactive streams is that you're like, I have this, say, database, and I want to get a stream of models from that database. I can nicely package that up in this thing called an observable and pass it like way across the code base. And that other thing on the other side of the code base can take this nice object, this object which I've passed around, which just represents a stream of data. With coroutines and launch, you don't have that. Like I can't pass you the execution context of this launch or something like that and have it operate somewhere else. But with Flow, you can do that. Flow becomes sort of the equivalent where like I can take this flow of data and package that up and have it somewhere else, and then that operates on coroutines. And so that may be why, like, even if you have an asynchronous single value, it may not be replaceable by coroutines, because that asynchronous single value might be provided and then, like, through some dagger graph that then, like, you don't have a coroutine way to provide that. Any other questions?
Is there any initial gotcha that like the first time you started writing coroutines?
Is there any other gotchas with coroutines? So many. But I am not here to talk about those. I'm still getting gotcha'd on a regular basis. It's hard. Concurrent code is hard. Like no matter which way you slice it, it's not easy, and you're gonna like cut yourself over and over again. That's just sort of like what we're trying to settle on is a simpler way to cut ourselves slightly less. But what I was focused on here was like, what really sucks is when you cut yourself and you have no idea why. The hope here is that like you cut yourself and you're like, oh, it's because I was thinking of it slightly wrong. Like my model was slightly off here. All right, I think we're at time anyway, so thank you all for listening.